welcome you all in today's NPTEL online certification course lecture on mechatronics. Today we are going to talk about digital circuits. Okay. So, digital circuits are part of every control system today. All the microprocessor, microcontrollers, computers all are operated with the help of digital circuits. So, in this block diagram for the components of mechatronic system, basically we are going to focus on the digital control architecture today, okay, and we will seeing the logic circuits. So, as I have been discussing with you earlier, analog and digital, these are the two types of signals which are available, and analog signal changes in a continuous manner actually, and the digital signals exist only at a specific level or state and changes its level in a discrete step, as you can see over here. And these digital signals forms actually the basis for the control of these modern electronic devices. The digital logics, basically these are controls which involves only two possible signal levels, okay. And as I said, digital circuitry is the basis for digital computer and microprocessor control systems. These circuitry evolved from the transistor circuits, which is being able to output one of the two voltage levels depending on the level of its input, okay. The two levels, namely it could be say 5 volt and 0 volt, are the high and low signal and represented by 1 and 0. So, the two levels of 0 and 1 may be what we can call it as either on off or open closed or yes no or true false, or by say plus 5 volt and 0 volt. So, this is how this that is 0 volt can correspond to say 0 signal and plus 5 volt can correspond to the 1 signal. Now, before we proceed, let us look at the number system, and this number system, various type of number systems, and with this understanding we will be able to operate the binary signals very proficiently. Okay. So, first of all, let us look at the decimal system. As we all are aware of this system is based on the use of 10 symbols or digits, that is from 0 to 9, as all of us know, and the digit position in a number indicates the weight attached to each digit basically, okay. And this weight increases by a factor 10 as we proceed from right to left, okay. So, this is how the weights are being attached, that is 10 to power 0, 10 to power 1, 10 to power 2, 10 to power 3, it is increasing in this direction as we are moving from right to left. So, suppose a general number is there, say this one, this number is actually equal to d n minus 1 into 10 to the power n minus 1, and here say d 2 into 10 to power 2, d 1 into 10 to power 1, and d 0 into 10 to the power 0. So, for example, if you have number 1, 2, 3, this is basically 1 into 10 to the power 2, 2 into 10 to the power 1, and 3 into 10 to the power 0. Okay. So, this way basically it forms what 100 plus 20 plus 3, and we get 123. 3. So, this is the decimal system by which we all are very well aware of. Next, let us see the binary system. This binary system is based on two symbols or state, that is 0 and 1. Okay. These are termed binary digits or bits, and when a number is represented by this system, the digit position in the number indicates that the weight attached to each digit increases by a factor 2, okay, as we proceed from right to left. Okay. So, here we have a factor, say the first digit will have a factor 2 to the power 0, second will have a factor 2 to the power 1, third will have a factor 2 to the power 2, and so on. Okay. So, these are actually, this is called bit 0, this is our bit 1, this is bit 2, and this is our bit 3. So, in general, if I have got say number, this one here the 2 subscript is used to indicate that it is in binary. So, this basically means that d n minus 1 into 2 to the power n minus 1, and here say d 1 into 2 to the power 1 and d 0 into 2 to the power 0. So, for example, if I have got a number, say binary number 1101. So, here basically this 1 corresponds to this one actually, okay, and its weight is 2 to the power 0. This 0 is actually this one with weight 2 to the power 1. This 1 is this one, okay, multiplied by 2 to the power 2, and this one is this one multiplied by 2 to the power 3. Okay. So, this is actually we can see that this is our 8 plus 4 plus 0 plus 1. So, this is 13 in the decimal system. So, the digits of a binary are called bits. The first or the leftmost bit is called the most significant bit, we call it in short as MSB, because it represents the largest power of 2. The last rightmost bit is known as the least significant bit, LSB, because it represents the smallest power of 2, and a group of 8 bits is called a byte. So, it is a little bigger, slightly bigger unit. Next is the octal system. So, this system is based on 8 digits, say 0, 1, 2, 3, 4, 5, 6, 7, 8, 7. Okay. So, these are the 8 digits, and when a number is represented by this system, the digit position in the number indicates that the weight attached to each digit is increases by a factor of 8 as we proceed from right to left. Okay. So, we have 8 to the power 0, then 8 to the power 1, 8 to the power 2, and 8 to the power 3. So, there is an increment of 8 that is by a factor 8. Okay. So, in general, if this is my number, so this is what is mean by it, d n minus 1 into 8 to the power n minus 1 plus d 1 into 8 to the power 1 plus d 0 into 8 to the power 0. So, number 15 in decimal system is basically number 17 in octal system. How? Let us see the 17 in the octal system. Okay. So, 17 in octal system basically means that we have 1 over here into 8 to the power 1, and we have 7 over here into 8 to the power 0. So, this is basically 8 plus 7. So, this is our 15, okay, in the decimal system. Next, let us look at the hexadecimal system. And this hexadecimal system, as the name indicates, is based on the 16 digit and symbols. Okay. So, these are 0 to 9, basically 10, and then A to F 6. Okay. So, 10 plus 6 16. So, based on these 16 digits and symbols, the hexadecimal system is formed. Now, in this system, digit position in number indicates that the weight attached to each digit increases by a factor of 16 as we proceed from right to left. Okay. So, here you have 16 to the power 0, then 16 to the power 1, 16 to the power 2, 16 to the power 3 and so on. Now, this system is generally used in writing the programs for microprocessor based system, since it represents a very compact method of entering data. Next, let us see the binary coded decimal system. Okay. The binary coded decimal, in the binary coded decimal system, basically it is widely used system with computer, and each decimal digit is coded separately in binary. Okay. Each decimal digit is separated is coded separately in binary. So, for example, 15 in binary coded decimal will be basically 0001 and 0101 like this. Okay. So, this is how it is going to be. All right. So, we can see that this is basically 1 and this is basically 2 to the power 2, that is 4 plus 1. So, this is 15. Okay. So, here the 1 is coded in the binary like this, and 5 is coded in the binary like this. Then the question arises, how do we convert from decimal system to binary system? Okay. So, it is a very simple, basically I can explain it by taking an example. Say suppose that 1 2 3 is in the decimal system and I want to convert it into the binary. Okay. So, what we do is actually we successively divide the decimal number by the base and record the remainder after each division. Okay. So, 123 I divide by 2 and I record the remainder. So, for example, 123 if I divide by 2, it will be 2 6 are 12. So, nothing is there, then 3. So, 2 1 ja 2. So, here I subtract it. So, I get 1. Okay. So, this 1 is basically the remainder and this 61 is goes for the next successive division. Okay. And now, I can do the division of 62 with 2. Okay. So, again similarly I can do that. So, 2 3 ja 6, this is 0 and so I get a remainder 0 and so I get a remainder 1 over here. Okay. So, this 1 basically comes over here and this 30 comes over here. Okay. And then again 30 by 2 is 0. So, this way I can keep on dividing and the last I get 1 by 2. Okay. And since this is not divisible, so remainder remains as 1. Okay. So, basically this 1 2 3 I can write in binary as this is my least significant bit. So, this will be actually 1 1 0 and 4 1. So, this is there. Okay. And so, this is how this can be represented over here. You can evaluate this using the formula which we have seen in the last few slides. Okay. So, this is 2 to the power 0 plus 2 to the power 1 plus this is 0 into 2 to the power 2 plus this is 1 into 2 to the power 3 plus 1 into 2 to the power 4 plus 1 into 2 to the power 5, okay, plus 1 into 2 to the power 6. So, this way we can 2, 3, 4, 5, 6. Yes. So, 0, 1, 2, 3, 4, 5, 6, and if you evaluate you will get 1, 2, 3. So, the reminders when written in the reverse order from left to right from the digits of the number represented in the new base. Next, let us look at the binary arithmetic. Okay. So, in the binary arithmetic, say 0 plus 0 is 0, 0 plus 1 is 1 plus 0 is equal to 1, and 1 plus 1 is basically 10, or that is 0 plus carry 1. So, I can see it here basically. So, say 9 plus 3 in the decimal system, this is 12, and 9 in binary is actually represented by 1001, okay, which is basically 2 to the power 3 plus 0 into 2 to the power 2 plus 0 into 2 to the power 1 plus 1 into 2 to the power 0. Okay, and this is what 0 into 2 to the power 3 plus 0 into 2 to the power 2 plus 1 into 2 to the power 1 plus 1 into 2 to the power 0. So, this is 3 and this is 8 plus 1 9. Okay. So, this is how it is. So, this is how we can add it. So, 1 1 0 carry 1. So, that 1 and 1 0 carry 1. So, that 1 is here and this 1 is here. So, this is 12 and this is basically what this is 0 into 2 to the power 0 plus 0 into 2 to the power 1 plus 1 into 2 to the power 2 plus 1 into 2 to the power 3. So, this is actually 8 plus 4, and so this is 12. Okay. So, this is how the binary summation is carried out. Likewise, we can also have the binary multiplication. So, for example, 9 into 3 is 27. So, this way 9 is your 1001 and 3 is 0011, and likewise as we do the normal multiplication we can form the table, okay, and then do the summation as using these three basic principle, and we can get the required number. Okay. So, here this is what we are going to get. Okay. So, you can check this must be equal to 27 in the decimal system. Conversion from binary to hexadecimal. Suppose I want to convert from binary to hexadecimal. So, binary number we have taken 1, 2, 3, okay, and for that 1, 2, 3 we have seen over here its representation here there are 4, 1, 0 and 1, 1. So, this is where 4, 1, 0, 1, 1. So, this is that number. So, for converting from binary to hexadecimal, what we do is actually we form the group of 4 bits. Okay. So, 1, 0, 1, 1 is formed together and only 3 1 are here. So, I put 0 from my side, okay, and then we write their decimal equivalent. Okay. So, for example, this is 7 in the decimal system and this is 11 in the decimal system. Okay. And so, the 7 in the decimal is written as 7 and 11 is written as B. Okay. So, this is its hexadecimal representation. Okay. So, this is how from binary we can convert it into that is hexadecimal. Okay. So, we divide the number into group of 4 digit beginning with least significant bit and replace each group with its hexadecimal equivalent. Next, let us look at combinational logic and logic classes. Okay. combinational logic devices are digital devices that converts binary input into binary output based on the rules of the mathematical logic which is defined. Okay. And these devices are also called gates because they control the flow of signal from input to the signal output. The truth table is a compact mean of displaying all possible combinations of input and their corresponding outputs. The algebraic symbol used to represent the logic functions are say plus for okay, logic R and dot for logic and overbar for the not, okay, denoting inversion. So, here are a table explaining the type of gate and the operation which is being carried out, how it is symbolically represented and what is the expression for that and what is the truth table for that. So, let us begin with that. So, first is the inverter, okay, or not gate, what we call it as. So, it inverts the signal. This is how symbolically it is represented, that is an amplifier signal with a circle at the vertex here over there, and the expression for this is, say, A is the input here. So, this is your input and C is your output. Okay. So, here this C is equal to A invert. Now, the truth table for this is like this. So, what is my A and what is my C basically. Okay. So, here is the input and here is the output. So, if my A is say 0, then its inversion will be 1, and if it is 1, then its inversion is going to be 0. So, this is going to be the truth table for that. Next is the AND gate, and operation is the AND logic. So, suppose this is the symbolical representation of that. So, A and B are the input and C is the output, and its expression is C is equal to A into B. Okay. And if I look at the truth table, okay, so again here A and B are the input and C is the output. Okay. So, here you see that if A is 0 and B is 0, you have C is 0. If A is 0 and B is 1, then your C is 0 basically. Okay. And if A is 1 and B is 0, then also C is 0, and if A is 1 and B is 1, then C is 1. So, basically this actually can also be explained with the help of, say, there are two switches, okay, like this. Okay. So, you are going to have output only when both the switches are on. Okay. So, here also the you are getting to the going to get the output only when both A and B are on. Okay. When both A and B are 1, then you are going to get the output 1, otherwise it is going to be 0 only. So, this is the AND gate. Next is the NAND gate basically, and it is nothing but the inverted AND gate, and here just this inversion is represented here by putting a circle here, and in the expression we put a bar at the top of it to represent the inversion. Okay. And here basically now whatever has been the AND output, that has to be inverted. So, the AND output for this has been 0, so inverted 1, here it has been 0, so inverted 1, here it has been 0, so inverted 1, and here it has been 1, so inverted 0. So, this is how the NAND gate is defined. Then let us look at the OR gate. The logic is OR logic. Okay. This is the symbolic representation of it. We have the two input here and here is the output. Expression for OR is given by C is equal to A plus B. Now, here let us look at this input side and output side. So, if A and B both are 0, then naturally your C is 0. Okay. If A is 0, B is 1, then output is 1. If A is 1, B is 0, then also output is 1, and if both are 1, then also the output is 1. Okay. So, this is basically what is mean by it. Okay. So, it can be symbolically or if you want to understand it, it is just like this actually, that you have a say switch here and you have a switch here. Okay. Both are in parallel. Okay. And say this is A and this is B. Okay. And you have the output over here C. So, you see that if both are open, then you have 0. If either one is closed, then you have the output, and if you both are closed, then you have the output. Okay. So, this is how it is, and then the NOR gate is the inverted OR gate. Okay. So, basically here you have the inversion, and the output here will be the inversion of this one. So, 0 inversion is basically 1 over here, and for the 1 inversions 0 is over here. So, that is there. Then we have the XOR gate, or what we call it as the exclusive OR gate basically. So, here say A and B are the input and C is the output over here. This is how it is represented in the expression, and this is what is mean by it actually, that is A and B inverse plus A inverse and B. Okay. And corresponding your table is going to be this one. Okay. So, here basically if either both are 0, both input is 0, then output is 0, and if both input are 1, then also output is 0, and if either input is 1, okay, then you have the sorry, if either of the input is 0, then you have the 1 over here. Then we have a buffer, basically the operation is increase output signal current. Okay. And here expression is C is equal to A. So, whatever A is there, the same C is there. Okay. And a buffer is used to increase the current supplied at the output when while retaining the digital state. This is important if you wish to drive multiple digital inputs from a single output. Now, coming to the integrated circuits, actually these logic gates which I talked to you just now, these gates are available at as integrated circuits. Okay. And circuits with their say 74 XX number are basically the TTL circuit, or what we call it as the transistor logic circuits, and based on the use of transistor and operate between 0 to 5 volt level. So, for example, you can see that the IC 7408, okay, this is based on the AND, that is, if you want to have the AND gates basically, then you can have the 7408 IC. Okay. And if you want to use the OR, so for OR gate purpose 7432, this is for AND gate purpose, and this is for inverter or NOT gate purpose. Okay. So, these type of ICs are available. Then combining of gates. Okay. All the gates as I just said are manufactured as ICs, okay, where transistor, resistor and diode exist in a single chip of silicon. Now, there are two families of digital integrated circuits. One is the TTL or the transistor logic, okay, and they have number 74 dash dash, and the other is CMOS for complementary metal oxide semiconductors, and voltage level divides logic low and logic high at the input and output basically, and CMOS have numbers 40 and so on. Okay. And high speed CMOS family have number 74, H is actually there, and then CXX. Now, let us look at the Boolean algebra laws and identities. So, there are some fundamental laws, okay, for say R. Okay. So, A plus 0 is A plus 1 is 1, A plus A is A, and A plus A invert is A. Okay. And for the AND, A into 0 is 0, A into 1 is A into A is A into A invert is 0. And for the NOT basically A is same as A invert. Okay. And there are commutative laws, that is A plus B is equal to B plus A into B is equal to B into A. Associative laws we have A plus B plus C is equal to A plus B plus C. So, either you can associate A plus B or you can associate B and C, and similarly A into B into C is equal to A into B into C. Then we have the distributive laws, A into B plus C is equal to A into B plus A into C. Similarly, for A plus B into C is basically A plus B into A plus C. Then there are De Morgan's laws basically. So, these laws are there to convert the OR operations into AND operation or AND operation into OR operation. Okay. So, here basically you can see that A plus B plus C all invert is equal to invert of individual ABC with the AND. That is with their multiplication, okay, or with the AND form, and A and B and C invert is equal to basically invert of A plus invert of B plus invert of C. So, here what we can see that here the AND has been converted into the OR has been converted into AND, and below the AND has been converted into OR. Then many times we used to draw the timing diagram basically. So, indicates that with respect to time how the signal what are the signal. Okay. So, it actually shows the simultaneous level of the input and output in a circuit versus time. Okay. And the timing diagram can be used to illustrate every possible combination of input values and corresponding output, providing a graphical summary of the input output relationship, and many times it does help us in understanding. So, for example, AND gate timing diagram. So, here say A and B are the input and C is the output, and as you say that this is the AND. Okay. So, here you see in case of AND, okay, for one to have you need to have both the signal as 1. Okay. So, AND is basically the two switches in series, that way you can understand. Okay. So, if this is A and B and so you have C. So, if both are 1 then only you will have C is equal to 1. So, you can see here A is 0 and here B is 1. So, and you are going to get 0 over here, okay. But at this place A is 1 up to here and B is already 1. So, you are going to have the 1 over here for the C. Likewise, I can explain it. Similarly, with the OR gate, for the OR one, it is as I have been as I explained to you. So, say this is if A, B and say your C is over here. Okay. So, here if your say A is 0, okay, and B is 1, then you are going to have C is equal to 1. So, you can see over here that C value is 1. Okay. Likewise, you can explain the OR gate for the using the time diagram. Now, after all these basic concepts, let us use these basic concept in designing of a logic network. Okay. So, for designing of logic network, the example which I am going to take, I have taken from Alciator and Histon book on mechatronics. Okay. So, those who want to read further, you may do refer that. Okay. So, for the design of logic network, there are basic steps we can formulate. First of all, say define the problem in the work. Suppose if you have to design a logic network, first you can define the problem involved and then you can write a quasi logic statement in English that can be translated into a Boolean expression. Okay. And then from that quasi static statement you write the Boolean expression. Okay. And then you can simplify and optimize the Boolean expression. Okay. Why do we need that? Because ultimately we are going to realize that with the help of some gates. Okay. And gates, how we are going to get? Gates we are going to get in the form of ICs. Okay. So, if you simplify that, then you are going you may require the few number of ICs or lesser number of ICs. Okay, to realize that particular Boolean expression. Okay. So, then we write an all and all NAND, all OR. Why do we do write this all type that is similar type of gates, okay, expression in terms of the similar type of that. Okay. That is because so that we need to use only similar type of ICs, okay, one IC rather. Okay, based on the requirement similar type of ICs. Okay. So, write an all and all NAND, all OR or all NOR realization of the circuit to minimize the number of required logic gates, ICs, components. And then finally, draw the logic schematic for the electronic realization of the circuit. So, let us take the security lock system. Okay. So, first of all we define the problem involved. So, suppose we want the alarm system for a house, okay, and we want that the system should create a high signal sounding the alarm for certain condition of the house sensor. Okay. Now, also we want the user to be able to select one type of the operating state. Now, there could be various type of operating states also, and we want the user to set which type of operating state the alarm system he or she wants to operate. Okay. So, let us look at these three classification. Suppose the user wants an active state when the alarm will sounds only if the windows or the doors are disturbed. Now, this state is useful when the occupant are sleeping. So, if the occupant is sleeping and there is some disturbance to the windows or door, one should get the alarm. Okay. The other state could be that an active state where the alarm will sound if the windows or doors are disturbed or if there is a motion inside of the house. Okay. So, this state is useful when the occupants are away. So, if occupants are away, so if say the thieves are coming are coming to the house by breaking the doors or windows, or if there is a motion also. Okay, because somebody breaking doors and window, and then if they are moving inside, okay, and nobody is there in the house. So, in that condition also there should be an alarm. And the third state could be a disabled state, where the alarm will not sound, and this state is useful during the normal household activity. Okay. Okay. So, suppose this is the vague requirement which I want, and now I want to design a system, a security lock system. So, I define the Boolean variable, say A is the state of the door and window sensor, okay, B the state of the motion detector, okay, which can detect the motion of the thief inside of the house, and Y is the output used to sound the alarm. So, Y is my output. Now, I said that my user should be able to pick any of the three state. Okay. So, for that I say generate a 2-bit code set by the user to select the operating state. So, suppose CD is 0 1, say if user sets 0 1, then operating state is 1, if user sets 1 0, then say operating state is 2, and if user sets 0 0, it means that the operating state 3. Okay. That is, operating state is 1 is that the door and window sensor are activated, operating state 2 is that when apart from door and windows sensor activated, there is motion detector also activated, and third is for the normal case. Now, so what is our quasi logic statement? Okay. So, the quasi logic statement could be like this: activate the alarm, that is Y is equal to 1 if A is high, okay, and code CD is 0 1. Okay. 0 1 we wrote for the first state. Okay. So, alarm should be there for fulfilling both these requirement, okay, that is A is high and the CD is 0 1, okay, or activate the alarm if A or B is high and code is 1 0. Okay. So, this is my quasi logic statement basically. Okay. So, what does this means? This basically means that output should be there if your A is high and the user had set code that he is not he is or she is sleeping, okay, or the alarm should be activated, that is if either doors and windows are disturbed or the motion of the person inside the house is detected, and the user had said that he is not in the house, that is the state 1 0. So, we can write the Boolean expression. Okay. So, to create a product of 1 for the Y product 1, because we want the alarm. Okay. For the active control code 0 1, we need to form the expression C invert D, because we have first state 0 1. So, if I want 1 product of 1, naturally this 0 1 I have to invert, this 0 I have to invert, okay, then only I can have 1. Similarly, to create a product of 1 for the other active control, say 1 0, okay, we need to form the expression C D invert. So, here I need to invert D, so that this 1 0 could be made 1 1. Okay. So, my expression output Y is this basically. What I have to create a AND operation with A and C invert D, okay, and then I have also AND operation with A plus B and C D invert, okay, and then I have the OR operation. Okay. So, this single expression basically is the representation for this Cauchy logic statement. Okay. So, this is the single expression is for that Cauchy logic statement. And now, here, basically as I said, we want alarm to be on. So, that is we want y to be 1, okay. And here our code was 0 1, that is why I inverted it over here to create 1 1, okay, and then I put the AND operation with A, and here we have we want A plus B over here, that is in either case here that is either A or B is high. So, I want the OR here. So, A plus B here, and then I have created here I want an AND operation with C and D invert, okay, over here. Okay. So, from the table I can see here that if my C is say 0 1 0, okay, and say D is 0 0 1. So, what is my C invert D? C invert D is basically 0. If C is 1 and D is 0, then C invert D is again 0, and if C is 0 and D is 1, then C invert D is 1. Okay. And what is my C D invert? So, if C is 0, D is 0, then this is 0. If C is 1 and D is 0, then D invert is going to be 1, and 1 into 1 is going to be 1, and in this case this is going to be 0. Now, if I look at this table, then you see that C invert D is 0 0 1, and this is same as D. Okay. So, what does this means? That I can replace this C invert D with simply D, okay. And here you see C D invert is 0 1 0, and here C is 0 1 0, okay, this one, alright. So, this is same as this one, okay, and this is same as this one. So, I can replace C D invert by C over here. Okay. So, this is my simplified expression for this. Okay. So, this is my simplified expression. Now, I want to convert it for making the AND realization. Okay. So, that I can do. So, first I take up this AND operation, I convert it into the I first take this OR operation, I convert it into a AND one, because I want the realization of AND, and in the next step I convert this OR operation into the AND operation. Okay. This is basically invert of individual that is A and B and its whole invert, and similarly here it is going to be the invert of this and invert of this and then whole invert. So, invert of this is this one and invert of this is this one, okay, and then you have the whole invert. So, this is the AND realization. Okay. And in the last we can draw a circuit diagram for this AND realization. So, suppose I have got the 4 inputs A, B, C, D over here. Okay. So, you see this is how it is done. So, we have the A invert, so I can take A from here, invert it over here, then here is actually, so this is actually what A invert basically, okay, and here I have got B, I put it an invert, so I have B invert. In the AND operation I get A invert dot B invert over here, okay. Yes, I have got this. Now, I have to take this whole invert over here. So, I put one NOT gate here. I invert this. Okay. Here is basically A invert dot B invert whole invert over here, and then I have C directly from here. Okay. And I take a product of that. Okay, I take a product of that. AND gate I use for that. So, this is my output. Okay. And after this what I do is that I take another invert. Okay. Here. So, for this operation, okay, and then I feed it to the AND gate to take it with A and D. Okay. So, here I have AND gate. So, I take A from here, A is here, D is here, A and D is here, I take invert of that. So, here I get A and D invert, and this A and D invert, and what is here is basically A invert and B invert and C and A and B invert basically. So, this is the input. So, here I get the output. Okay. So, I get the multiplication or AND operation of that, and then the whole invert. So, basically this is my Y which is equal to this one. Okay. So, these are the references for you can look at Alciator and Histand, as I told in the beginning. For this you can refer other two books also mentioned over here. Thank you.